So what we're doing, we're revisiting quadratic functions. And again, these are going to be of the form. Now we're going to use the functions notation for these. But ax squared plus bx plus c. And again, we want to be able to identify what a is, b is, and c is. So for example, for something like this, a is always going to be the number in front of the x squared. And so what that's going to mean is that a is going to be that invisible 1. And then in front of the x, b is a -1. And then with 2, that's the constant. And then if we have something like this, it might be a little more identifiable if we have something like this. So in this case, a is 4, b is -2, and c is +1. Now, we talked about graphs, and we talked about graphs of lines. So now what we're going to get into in this section, we're going to be looking at graphs of parabolas. So the parabola it's going to be the graph of a quadratic function. And what it looks like is usually something like this, or something like this. Depending on which kind of quadratic function we're looking at. Now, there's sort of an, I guess you could say, an anatomy to these things. So let me just kind of go over that. I'll come up, let's see, let's get a typical one here, a relatively typical. Well, let's say we have this. So if we were to graph this parabola, and then let me think about this. Might want to make a modification here. Let's change it to this. We'll do that. Something like this. Let me double check some math here. Okay, we're good. So this point here, where the graph sort of does its turning and it goes in the other direction, we call that the vertex. And then the line passing through the vertex, a vertical line. This is the axis of symmetry. So we have the vertex and the axis of symmetry. Now, define the vertex. There's a formula. Now again, the vertex is a point on the XY plane, or rectangular plane. But this is the location of that vertex. So what we'll do to locate the vertex, we take our quadratic function, we identify A, B, and C, and then the x coordinate will be the B divided by 2 times A, and then we put a negative sign on there. We take the opposite. Then we take this value, plug it into the function f, and that's going to give us our y coordinate. So let's take a look for this function. So any questions about that? All right. So for our function here, A is equal to 1, B is -4, and C is equal to 6. So negative B over 2A is going to be negative, there's B, over 2 times 1, or 4 over 2 over 2. So that's going to be our x coordinate. And then f of negative B over 2A will be f of 2 which will be 2 squared minus 4 times 2 plus 6. Over 4, we'll get 4 minus 8 plus 6, or -4 plus 6, and again it's going to be 2. So the vertex will be 2, comma 2. And that's going to be your answer. So questions about that? Right. So there are 2 other parts about the, well, another thing we could mention, we could ask this: what would be the vertical axis, or the axis of symmetry? Well, recall that the axis of symmetry passes through that vertex. So in this case, it's a vertical line. Two comma 2. And so that's going to be x equals 2. Now, the other 2 things we ask about for parabolas is going to be where they cross the x and y axis. And sometimes they don't cross the x-axis. That is possible. But let's take a look at y-intercepts. Or where the parabola crosses the y-axis. Well, for something like this, the way we're going to find this, they're going to find it exactly the same way that we find the y-intercept for a line. So what we'll do is we'll let x equals 0 and solve for y. So back to our parabola. We'll rewrite f of x as y. And again, f of x and y are interchangeable. And we're going to let x equal 0. So we're going to get 0 squared minus 4 times 0 plus 6. And these are just going to be 0. So we're going to get y, this is 0 minus 0 plus 6, which is going to be 6. So what this means is our y-intercept, x was 0, and when it is, y is going to be 6. So that's how we find the y-intercept. Now, the x-intercepts are going to be a little different. Well, I gotta be, as far as the procedure goes, it's going to be actually the same as lines, but the process we're going to go through is going to be different. But it's one that we've seen before. The nitty-gritty, as they say. So just like with lines, to find the x-intercept, we just let y equal 0. And we solve for x. But since we're dealing with quadratics, this is most likely going to mean we're going to bring back our friend, the quadratic formula. Now you could use factoring too. We had looked at that. And so what we're going to get is f of x, which equals ax squared plus bx plus c. And I'm going to solve a different quadratic first before we solve the one we've been working with. Then you're going to solve this equation. And again, you could use factoring, you could use the quadratic formula. If you're not sure about factoring, quadratic formula will get you through every time. So any questions about that? All right. So for example, so let's say we have something like this. Well, again, what we're going to get make f of x and the y, and we put y is equal to 0, we're going to solve for x. Now I'm going to use the quadratic formula. So here a is going to be 1, b is -5, c is 6. So any questions about that? So going back to the quadratic formula, x is negative b plus or minus square root of b squared minus 4ac divided by 2a. Or negative 5 plus or minus square root of c, negative 5 squared minus 4 times 1 times 6. And then 2 times 1. So for b, b's negative 5, so we replace b with negative 5s. A is 1, so we replace the a's with 1s. And then the c is 6, so replace c with 6. So negative and negative is a positive. Negative 5 squared is 25 minus 24 over 2, or 5 plus or minus. This will be square root of 1 over 2. And we'll get 5 plus or minus 1 over 2. So that's going to break up into 2 results. When there's a plus and when there's a minus. So for the plus, we'll get 6 over 2, or 3. For the minus, 4 over 2, or 2. So when we solve for x, when y is 0, this is an x, and this is an x. So since y was 0, we call this, we set y equal to 0. So that means our x-intercepts, I'm going to abbreviate intercepts, it's going to be the point 2, 0, and 3, 0. Those are going to be your answers. So what's going on here? Well, let's take a look. We found the x-intercepts for this parabola. So let's try graphing it. This is kind of one of the trickier parts to do. So let's take a look. I'm going to write this off to the side. We have x-intercepts of 2, 0. So let's find the y-intercept. Now recall, for the y-intercept, we're going to let x be 0 and then solve for y. So we'll call this, instead of f of x equals, y equals. So for y-intercept, x will be 0, 0 squared, plus 6. And so once again, we're going to get y equals 6. So this is going to mean, since x was 0, it's going to be 0, comma, and then now y is equal to 6. I'm going to put this over here. So we have the x-intercepts. We now have the y-intercept. Let's find the vertex. So any questions about that?
I haven't gotten all the answers written down yet. I was just gonna give me a second so I could get that really fast.
No problem.
Thank you.
Okay.
Okay, go ahead.
No problem. So we want to find the vertex. So when we're graphing these, we want to keep an eye on our x-intercepts, our y-intercept, and then our vertex. So that's going to be negative b over 2a, comma, f of negative b over 2a. So for this one, I'm going to write the quadratic using f of x instead of y. It's going to be x squared minus 5x plus 6. So in this, a is 1, b is negative 5, c is going to be 6. So negative b over 2a, well, that's going to be negative 5 over 2 times 1, or 5 over 2, or 2.5, 2 and 5/10. So that's going to be the x coordinate of our vertex. I'm going to write that off to the side here. Now you could also call this 5 halves, because 5 divided by 2 is 2.5. Now for doing the calculation, I'm going to use fractions just because I think a little better in fractions. At least that's what I tell myself. Now, is it okay if I erase this? I can wait. Okay. So in this case, we're going to do f of 2.5 equals f of 5 halves, which is 5 halves squared minus 5 times 5 halves plus 6. This will be 25/4 minus 25, not an equal sign, 25 halves plus 6. So I'm going to give everything a common denominator of 4. This will be 25/4 minus, now I want a 4 on the bottom here. So to do that, I'm going to multiply bottom and top by 2. And then for this, we can rewrite 6 as 6 over 1, because 6 divided by 1, that still gives you 6. But to get a denominator of 4, I'm going to multiply bottom and top by 4. So we're going to get 25/4 minus 50/4 plus 24/4. We'll get 25 minus 50 plus 24. We can have these all divided by that common denominator. The power of your common denominator lets you do this. So what this is going to turn out to be is -1/4. We're going to keep the denominator, and then 25 minus 50 plus 24, that's going to be -1. Or as a decimal, -0.25. Squeeze this in there. So this is going to be the y-coordinate of our vertex.
Which would you prefer, the -2.5, or did you prefer the -1/4?
Oh, well, the 2.5. Oh, for the answer, I want to say either one. For this, God, I'm not actually sure what Cengage is going to do. It should accept both answers. If it doesn't, if you were to say put -1/4 instead of -0.25, let me know. I can give you credit for that. That's going to be fine. Though the one thing with decimals you want to be careful is if the only way you could put a decimal answer in is if you had to round it off when they wanted an exact answer instead, because we consider decimals approximate answers and then the fractions exact. So if you have like a repeating decimal or an infinite decimal and you rounded it off when the problem wanted the exact answer, then you would miss it. But I guess the safest thing in that case would be to go with -1/4. That would be the safer thing to do. So I would say for my vertex here, you might enter 5/2 -1/4 instead of 2.5 and -0.25. Though to be honest, for graphing purposes, I think people tend to think more in terms of the decimals than the fractions. Like you can usually point out 2.5 on the number line, not always 5/2, but they're the same thing. They're equal to the same thing. This was just a little less familiar.
Okay, that'll work.
Now, is it okay if I erase this?
Yes, I just realized that you could turn it into a decimal to find a better solution. It's a little bit more clear that way.
I think it is. I think it's just when you're working with number lines, you usually graph decimals. I mean, sometimes you'll graph fractions, but I think most students graph decimals, not fractions as much. So this might be the answer you put in for like in the answer blank, but you would convert it to a decimal to make it easier to graph. So if we graph this thing, well, let's start off with the x-intercepts. So way back when we found the x-intercepts, and this is where the function or parabola crosses the x-axis. So we have 2 and 0 and 3 and 0. Now the y-intercept is 0 and 6, or where the parabola crosses the y-axis. So that's going to be way up here. Finally, the vertex, it's 2.5, -0.25. Now 2.5 is in the middle of the 2 and 3. And then the y coordinate, it's just like this is negative 0.5. This would be negative 0.25. Put it right about there. And so what we'll do, we'll connect these points to get our parabola. And that's going to be our answer. Put some curly braces here to emphasize this is the exact same point as this. Decimal version, fraction version. And so that's going to be it. So questions about that? So
Just super quick, like in a parabola's case, we're only using, is it the y? Is that y? Or oh, never mind. I get, okay, sorry.
oh, no
Because
worries, no worries.
on the negative 2.5, because we have, it's x, y, so it's 2.5, and then we have the, okay, I get it
Right.
now. Okay.
No problem. So that's this parabola. Now, I mentioned a while ago, this is different from that one we were working with before. And I want to talk about the one we worked with before, because the graph for that one, that was, if you recall, we had f of x was x squared minus 4x plus 6. So for that, if you recall what the graph looked like, the parabola was kind of floating in space. If we think about it, with this branch going up and this branch going up, it's never going to cross over the x-axis. So if you try to find the x-intercepts for this, what's that going to look like algebraically? So this never crosses the x-axis. So how do you, when you're looking for the x-intercepts, but this doesn't have any x-intercepts, what does this do to our quadratic? So we're going to try to find the x-intercepts on this quadratic function that doesn't have any x-intercepts. And this is where that concept called the discriminant comes in. But let's try to do it. See what happens. So once again, we look for A, B, and C. A is 1. B is -4. C is going to be 6. And we're solving. 0 is x squared minus 4x plus 6. So negative b plus or minus b squared minus 4ac divided by 2a, or -4 plus or minus the square root -4 squared minus 4 times 1 times 6 over 2 times 1. 4 plus or minus the square root of 16 minus 24 over 2. And this is where we're going to start to see things kind of indicate that we're not going to be able to find x-intercepts, because this is going to be the square root of -8. And since we're dealing with what are called real numbers, these are fractions, decimals, we're avoiding the so-called imaginary or complex numbers. In this case, this is not a real number. And so what happened was, if we just take a look at the square root, the inner part is less than 0. Or put another way, b squared minus 4ac is less than 0. So then this is what was called the discriminant. So when this happens, when the discriminant, in other words, what's inside the square roots, when this turns out to be less than 0, that means there are no x-intercepts. So just something to keep in mind. When you get a parabola that's sort of floating above the x-axis like that, that means if you compute the discriminant, you're going to get one that's less than 0. That means you'd be in the quadratic formula, you'd be trying to take the square root of a negative number. And in this situation, we can't do that. Now, again, if you allow for complex numbers, that's okay. But when this happens, that means you don't have x-intercepts. Questions about that? So another one I want to show you. So we've seen two of these now where we have no x-intercepts and then where we have 2 x-intercepts. It is possible to have only 1 x-intercept. So it's going to look very similar to the one we just did. And so we'll try to graph this one. So again, let's look for the y-intercept. And again, to find the y-intercept, we're going to let x equal 0 and solve for y. It's 0 minus 0 plus 4 is 4, 0, comma 4. So that's the y-intercept. Now, let's look for the x-intercept. In this case, we let y equal 0 and we solve for x. And what we're going to get is a quadratic. Well, we have a quadratic, but this is a quadratic we can use our quadratic formula for. And we're going to get a is 1, b is -4, and c is +4. So once again, x is -b plus or minus the square root of b squared minus 4ac divided by 2a over -4 plus or minus the square root -4 squared minus 4 times 1 times 4 divided by 2 times 1. So we're going to get something interesting on the inside. We get 16 minus 16 over 2 4 plus or minus the square root of 0 over 2. So what this becomes is just 4 over 2. Because if you plus or minus 0, square root of 0 is 0. And whether you add 0 or subtract 0, nothing changes. So we get x is equal to 2. So letting y equal 0, we get an x of 2. So we only get one x-intercept. So the reason is when you're discriminant, when that equals 0, you get one x-intercept. So the last thing to figure out is the vertex. I'm going to rewrite this so I can see it. So -b over 2a. It's -4 over 2 times 1, or 4 over 2, or 2. And that's the x-coordinate for the vertex. And then f of -b over 2a, this is f of 2, or 2 squared, minus 4 times 2, plus 4, or 4 minus 8 plus 4, we're going to get 0. So the x-coordinate is 2, the y-coordinate is 0. So take a look. With this one x-intercept, it's the same point as the vertex. So if we graph this, give me a second to write that down. Is it okay if I erase this?
Sure.
Okay. Yeah, whenever you're ready. So the y-intercept is here. The one x-intercept and vertex are right here. So we can graph our parabola like so. Put a little more arc on this. And there we go. So the point is, with these three parabolas we've looked at, you can have a parabola that has two x-intercepts, a parabola with one x-intercept, parabola with none. So let me summarize that. And it all goes back to the discriminant. We're going to look at this part of the quadratic equation. So when this is greater than 0, there are two x-intercepts. Now when it's equal to 0, there's one x-intercept. And when it's less than 0, there are no x-intercepts. So just something to keep in mind when we're dealing with these functions, these quadratic functions. If your discriminant, what's inside the square root, is greater than 0, you're going to get the two x-intercepts. When it equals 0, you'll get the 1. When it's less than 0, there are no x-intercepts. You have your floating parabola, I guess. It's not anchored to the x-axis in some way. So questions about that? So the last thing to mention in this section, it's an application, and it has to do with the vertex. And so what it is.
Okay, so I'm so sorry. I had a question.
Sure.
Okay, so when we were getting the first round of answers, we got 0, 4, and then we have 2, 0. And I was just trying to figure out how we got the second 2, 0, because I was following along and then I realized
that was the vertex. It turns out for that parabola, your vertex and your x-intercept are going to be the same.
Okay. Gotcha. Okay, cool. So that would be okay. Thank you.
No problem. And we're going to do some more stuff with the vertex. For applications, the vertex can be a maximum or a minimum. So if you have sort of a, what would, for us, given our examples, a flipped over parabola, and this is our vertex, this is the highest point on that parabola. So this would be a maximum. And then on the parabolas we've been looking at, we've been graphing, here the vertex represents a minimum. So I'm going to pull a question from the homework here. Let's say we have this. Take a sip of water, give you a second to finish copying that down. And is it okay if I erase this?
Yes.
All right. So let's say we have this. So let's let h of t equals negative 16 t squared plus 64t plus 50 be the height of a ball that was tossed upward initially at 64 feet per second. From a cliff $50 feet above ocean beach. Now here t is seconds. let's find the maximum height of the ball. So we've got this formula for the height. You can kind of piece it together. You can kind of see what's the parts of the problem in the formula. The 50 feet above the beach, that's going to be that 50 there. The 64 feet per second is going to be that there. This is actually related to gravity. The pull of gravity, the acceleration due to gravity, it's going to be working in the opposite direction of the ball's path, or at least it's going to be working the opposite direction of the direction we've tossed the ball, because we've tossed the ball upward. It's 32 feet per second. And the way this formula is derived, use calculus to derive it. So you end up getting a 1/2 times the 32. And that's how this becomes a 16. And again, that 1/2 comes out of the calculus that you use to derive this. And then the negative on the 16 tells you that the ball's traveling upward, but gravity is working in the opposite direction, or we call the negative direction. So that's where that negative is coming from. So what happens here is it okay if I erase this?
Yes.
Now, sort of a tip I can give you. Let's say we have something like our generic quadratic equation. If we have a less than 0, we're going to get that flipped over parabola, and this is going to be a max. And if a is greater than 0, we get the parabola we've been working with the most, and the vertex is going to be a minimum. So now they told us we're looking for a max, but to verify that mathematically, or just to kind of see maybe another clue, a is negative 16. So a is less than 0. That means we're definitely going to be, the vertex is going to represent a maximum. So the vertex will give us the maximum. So instead of x and y, or x and f of x, we're going to be dealing with t and h. So the t coordinate of our vertex, well, it's still negative b over 2a, or negative 64 over 2 times negative 16, or negative 64, negative 32, and that's going to be 2. And then h of t will be h of 2 negative 16. 2 squared plus 64 times 2 plus 50. Two squared is 4. 4 times 16, negative 64. 64 times 2 is 128. Add 50. Or add these two, it'll be 64 plus 50. And that's going to be 114. So what this tells us is that the vertex this max vertex is time 2 seconds and height 114 feet. And since we were asked about the height of the ball, the max height is 114 feet. And that's going to be it. So any questions about that? Let's see. So let me do one more. So this time, let's look for a minimum. Is it okay if I erase this?
Yes, it's okay.
All right. So let's say we have this. A cost function representing the cost to produce. Let's see here. I'll pull another homework question. Camera lenses is C of x 0.1x squared minus 20x plus 2000. So for this one, find the number of lenses x where cost is a minimum. So a cost function, you're trying to figure out what the costs are for your manufacturing. There's a lot of things that go into cost. You have what are called fixed costs and what are called variable costs. Fixed costs are costs you're going to have even if you don't make anything. So for example, rent is something you're going to have to pay regardless if you're manufacturing something or not. Any licenses or things like that, so you could manufacture if you decide to, You got to pay for those, things like that. Basic heating, like for people to just maybe show up to work, and even if you don't put them to work, you don't want them to freeze. So, and then there's like insurance costs and stuff like that. So those are your fixed costs. And then you have variable costs, and these are the costs of like materials, the amount of electricity going into, say, the production machinery, the maybe repairs on the machinery, increased electricity due to warming more of the building up because people are using more of it. So those are your variable costs, and that gets sort of summarized in this function. And the idea is that the more you produce, you can increase your costs. You're going to be getting, for example, using more materials. So you have to buy more materials. So it's going to increase your cost. So for this, if we take a look at this cost function, our A is 0.1, which is greater than 0. So this means we have this kind of a parabola, and the vertex is going to be a minimum. So if we find the vertex, we're going to find the minimum of this cost function. So x, remember x is the number of lenses, negative b over 2a. Now if we take a look at our function here, b is negative 20. So you have negative 20 divided by 2 times, and then a is that 0.1. Or 20 divided by 0.2, let's see, it's going to be 100. And this is actually our answer, because what they wanted to do is they just wanted to find the number of lenses. So x is the number of lenses. So the minimum will be the x-coordinate. What we're looking for is the number of lenses, or the x-coordinate of this vertex. So the answer is going to be x is 100. If you wanted to actually find out what the minimum cost is, you'd plug this back into this function, and that's going to give you the minimum cost. So questions about that? So that's it for section 10.4. If you have any questions about that, let me know. And that's going to be it. We'll look at exponential functions on Thursday, and those are really neat. Those are kind of fun. And but that's going to be it for today.